in the past year. So we are really growing fast, and it's a great opportunity also to work in this field. This is a fabless design house which design both software and hardware, mainly for HPC and AI. So let's start talking about, because this is the topic of today, regarding the vector computing, the basics of vector computing. Let's take a quick background before. On the right, you have a very well-known picture regarding the trends in the microprocessors in the latest 50 years. I don't want to go through all the details of this picture. It's just to understand why we need vector computing. In the past years, in the 70s, 80s, we started with a single core processors. And the way we were increasing the performance, because there is always a growing demand of performance for microchips, was to increase the frequency. And it was possible because of what is called the Dennard scaling, which is you can increase the frequency because at the same time, when you change the technology node, you reduce the voltage, and then reduce also the capacitance of the transistors. And for this reason, the dynamic power will stay the same, because one of the problems of the chips is to dissipate the dynamic power. But at a certain point, this formula was no more valid, because you cannot increase anymore the frequency, because you cannot scale anymore the voltages when you reach a certain technology node, because you are very close to the threshold of the transistors, and so the leakage power comes up and then increase the dynamic power. So the way was try to think differently, and then it was the idea to start with the ILP, which is the instruction level parallelism. Let's try to do something in parallel to reduce this this power. And this was also because people understood that the world is dominated by the data parallelism. And so the idea was, as we cannot increase anymore the frequency, we could go to a different level. So we can increase the parallelism. And at a certain point, we discovered also that it's better to go towards a heterogeneous computing. So it's better to build structures which are dedicated to specific computational tasks. In this field were born the SIMD, the GPUs, and also the vectors, which is the architecture we are going to deal today with. When we talk about target workloads which want to face with data parallelism, which are these high data level parallelism which we encounter. First of all, the AI and the machine learning, which are the things which are very, very common now. Why we have a high data level parallelism? Because in this field you have to do many multiplication between matrix or vector multiplication, or another kind of multiplication which is called accumulate. You multiply and accumulate in local registers. And this is a high data level parallelism because data are independent. You can do all the operation, all the multiplication between vectors or matrices in parallel. So you can take advantage of this way of computing to build very powerful unit. And there are other examples of high data level parallelism workload, like image processing, and other things like this one. In image processing, you also, for example, have a picture. You have to do some filtering on the image, so you have to do the same operation on many pixels of the picture. So, and you can do these things in parallel. So let's start from just to have a common background. So what's the step from a scalar processor to SIMD processor? And now we will see what is a SIMD processor and vector processor. Very, very simply, in the scalar processor, you have an instruction from the processor going to a computing unit, which could be an adder, for example. And you have the data from memory, which goes into the scalar registers, and the results go in another register, and then you put back the data in the memory. If you have to do these things many, many times because you have a high DLP, you have to send many instructions to this simple unit, and it takes a lot of time. So an improvement where the SIMD architecture, when you do the same stuff, but the registers are bigger, in the same register you could put more than one data. And so with the one single unit in one clock cycle, you can do an operation between multiple data. And of course, you put the data in the target register and back to memory. The power, instead of the vector unit, which is the third picture here, is that you have these big registers where you can store a big amount of data, but also you can decide the length with this parameter we will see better later on, which is VL, the vector length. You can decide how many data you can put in there. It is very flexible, and because you can decide also how many computing units you can put here. You can have the flexibility to decide how many units you will put here, and so create a more powerful or a less powerful hardware. And then comes also the concept of lanes, because you can think to divide this big vector in pieces and put each piece in one structure, which is called lane, which can do the computation. And if you want to increase the number of data, you just increase the number of lanes, and you can extend this hardware as much as you can. So let's talk a little bit, just as background, about the RISC-V vector implementation. First of all, what is the RVV? RVV is the extension of, one moment, because, okay, I jumped a slide. So first of all, what is RISC-V? I guess all of you know RISC-V, so probably we can just go very fast on this slide. It's an extensible open source instruction set architecture. You can start from a very simple instruction set, which is, for example, this one, RISC-V 32-bit, which just handles integer operation. And then you can add a module. For example, if you want to do operations with floating points, you just add a new set of instructions which deals with floating points, and so on. At a certain point, you can add also this extension, which is the vector extension. And you have this kind of nomenclature here. RISC-V 32, for example, I stands for integer, M it's when you add the multiply extension. And if you want to add the vector extension, the things we are talking today, you just add the V to the description of the hardware. So this is a very modular design. Instead, let's talk about the RISC-V vector implementation now. It's a scalable vector extension because we saw that we can decide the length of the vector we will see later on at runtime. So we don't need to know how big is the vector register where we want to put the data inside the vector unit. And it allows to do the parallel data processing. This feature regarding the fact that you don't need to know when you write the code the dimension of the vector length. It's called the VLA, vector length agnostic. So the code you write does not depend on the dimension of the vector. And this is very different from the SIMD unit you saw from the picture before, where you know how many data you can put inside a register in a SIMD unit. And this is not that many flexible. The main structure of RISC-V vector register architecture is this one. It is composed by 32 registers. You can choose the VLAN, which is the length in bit of the registers. You can have short, long vectors, and so on. And you have a few parameters. You can choose. One of these one is the SCW, which is the select element width. So you decide inside the vector register the size of the data you are dealing with the next operations. And the LMAL, which allows you to group some registers to have a bigger register. And also you have another feature, which is the mask register. And you can use just the V0, just the first register, to put inside some data to mask the element or the vectors you are going to do the operation with. All these parameters then are put in a control register, which is a register which is not in the vector unit, but it is in the main processor in the scalar unit. Sometimes it is also replicated in the vector unit, but the real position is in the scalar unit. And you store some information like the vector length. Let's focus on VLAN, VL, which looks the same but are different. This is in bit. This one is in elements. So it depends on the size of the element you are storing in the registers. In this V-type, you put this information, the SCW and the LMAL. And there is also another field, which is V-start, which is used when there is an exception, for example, of the processor. You, instead of repeating the operation on the all data elements of the vector register, you can restart from the last computed one. So this is a recap of what we already said. The main concept, we can skip this one. Just focus on the real beauty of this kind of architecture, which is the vector length agnostic. For what you could write your code and have the code which runs on different implementation, on different hardwares. If your hardware is more powerful, it runs faster. It is less powerful, it runs slower, but in any case, the same code will work for both hardwares. Okay. We already told about this one, the VL, which is the number of elements inside a vector register, which can be changed at runtime. Your code could change the vector length, adapting to your need. If you want to do operation with bigger data, you change the VL to a bigger data, or you can reduce that. And it allows also to do a very easy handling of the loop tails. Loop tails are when you have a big vector which doesn't fit inside a vector register, you split the vector in pieces, and the last piece is smaller, and this is the tail. And you can manage in the same way also the smaller vector. This is just a summary on what the SCW mean. Very simply, this is a 128-bit vector. This is the vector length. If you choose, for example, SCW 8-bit, you have 32 elements in this vector register. If you decide to set the SCW in 16-bit, you have a reduced number of elements. You have 16 elements. And this is the concept of LMAL. You have 32 vector registers. If you are choosing, for example, SCW 8-bit, as we saw here, you have a register with 32 elements. But if you put LMAL equal 4, you have a bigger register which is composed of 128 elements. So this feature gives you more flexibility to deal also with the very big register. Even though if you use very big registers, you consume, you have 32 registers. So you have to take care of the number of registers you are using when you write your code. Okay, this is the concept instead of masking. It is very, very, very simple. In V0 vector, this is the same example of before. If you put 1 here, you are masking, for example, the first element is 0, you are masking this element, so you don't do operation on this data. If you put 1, you are saying, okay, compute the second and the third element. For example, in this case, if you want to do A plus B equals C, you are just saying, I want to add the second and third and the fifth element, sixth element. This is more or less the code, for example, A plus B equals C. But we will not go through all this stuff. The most important thing is this one. When we, for example, want to add these two vectors, A and B, A is put in B1, B in B2, and the result is put in B3 vector, we just, these are the instructions to take the data from memory. It's not important. We do this kind of operation. We add B1 and B2 and put the result in B3. And this is the mask, V0.t, which stands for true. In this case means just do the operation through. It means where you find the 1 in the mask. You can use also the reversed mask, putting F instead of T in this instruction. This is the summary of the main instruction types you can have in RVB. So a quick recap. I will not go through all these instructions, but we have many categories. The first one is the vector load and store. These are the typical instructions to take data from memory. And there are many flavors. You can take data in unit stride. It means the data are sequential in memory and you take the data one by one, or with a certain stride, certain step. Or with index, you can decide to take the first, the fifth, the sixth in the way you prefer. And there are other flavors. Of course, you have arithmetic and logical operation. What you want to do with the vectors is to put data in one vector, another data in another vector, and for example, sum the vectors, or do a logical operation, do an XOR between two vectors, an AND, and so on. You can treat both integer and floating point. It depends on the computing unit you put in your vector unit. The ISA allows you to do any kind of operation, both for integer and floating point. If you want to do floating point operation, you need to put in your vector unit also floating point unit to do this kind of operation. You can do the reduction operation, which are operation inside a vector. Reduce because you start from a full vector. Then, for example, you can sum all the elements of the vector, and it will return just one scalar data. And this data, unfortunately, is put in one vector because it's a vector unit. You cannot put this in a scalar, but then you can move this data to a scalar value. And you can do also other operations. The permutation slides are the set of operations which takes the data in one vector and move the data in the way you want. So you can shift, slide up, slide down, or compresses the operation when you have many zeros in the vector, and then you compact all the non-zero element in the first part of the vector, or shuffle, move the data inside the vector as you prefer. The masking, we already saw the masking, which uses the V0 register to mask the data for an operation. And this is not really a vector operation, but this is a configuration of instruction which set all the parameters we already saw. We didn't see the TA and the MA, which are two parameters which set the tail agnostic and mask agnostic feature. Tail agnostic means when you have a vector A, you don't use the full vector. What I have to do with the not used element. You can decide if you put TA equal to 1, you are saying, I don't care about what you are doing with the remaining element. So you can do whatever you want. It is, from a hardware point of view, the simple things to do. Otherwise, you can put TA equals 0, and you are saying you have to leave the tail undisturbed. You don't have to change the remaining, the unused elements. Let's see some architecture details. I want to summarize here very briefly some differences between a vector architecture and a SIMD architecture. And why we have more flexibility and more performances if we use vector architecture. SIMD uses fixed width registers. We have some examples in x86 and in ARM. x86 uses some extension which are called SSE, which use 120-bit registers, or there are other extensions. I just reported a few of them there. Or we have also this SIMD extension in ARM, the Neon extension, which has, and we have this extension, which is the SVE. Probably there are other extensions which have bigger vectors, and some of them are very similar to vector units. So it's very close to a vector architecture. But the beauty of the vector architecture is the one we already talked before. We have a theoretically unlimited vector size, because you can create an hardware which can handle a very big vector, even though the standard, the specification allows you just to use at most 64 kilobit register. So if you have a bigger vector, the performance will be bigger, but as I told you before, the code will run in any case. Okay, I just, to be sure it's what we told so far, it's clear, I just put two examples of, on the left you have an example of a sum of A plus B, equals C, a code which sums two vectors. In this case, it is done by RISC-V vector unit. This is the code for a RISC-V vector unit. And that one, it's the code for a SIMD unit. The example is for an x86 with AVX 256 extension. So the register in that SIMD extension are 256 wide. We will see better this one, and just a brief, quick hint on that one. Here you see, first of all, you can see the code here is very small, and there is a bigger one. And not only this one, this code will run, as we told before, on every kind of vector unit. That code will run just only on an hardware with AVX 256 extension. If you use this code on a different hardware, or you have to rewrite the code, or the code will run without taking the advantage of a powerful hardware. We will see better later on. So let's see this code. What you do here, every kind of vector instruction starts with this instruction, vset VLI, which sets the characteristics of the vectors you are going to deal with your operation. So if you want to do a sum, before you have to do every time this kind of operation, you have to set the number of elements, the type of elements, and so on. For example, in this instruction, you are saying, I want to have 32-bit elements in the vector. I'm using lmal equal to 1. And these are the two important parameters which exploit the power of the vector length agnostic of the RISC-V vector. In this register, you put the number, it is called very often AVL, stands for application vector length. You put the number of elements of the vector you want to do operation with. It could be also a very big number, even bigger than the maximum elements you can put in your vector register in your unit. And the hardware replies in this register with the numbers of elements it can process with every instruction. So this structure is very simple, because every time you do an operation on T0 elements, and then you will update A0, subtracting the number of elements you already processed in the previous loop. You can do this loop many times, and when you reach the end of the loop, you will deal with the tail, which is probably a reduced number of elements. You are not filling the vectors, but in any case, this same loop will work also with the tail. And then there are very few instructions. 2 instructions here to load v1 and v2 from memory. These are the pointers to memory. Then this is the add operation. You want to sum v1, v2 and put the result in v3. And then you store back the result in memory. These are the instructions to update the pointers in memory to do another loop. And it's very simple. In this case, we don't want to go through all the code, but it is bigger because, first of all, it depends on the size of the register. In this case, you want to deal with 32-bit elements. So you have 8 elements inside these 256 registers. And you see also here you have a reminder calculation, a reminder loop. And you have to do this, and also in the reminder loop, you cannot treat anymore the tail of your operation with the SIMD 256 instruction. You probably should go to scalar, using the scalar registers. In this example, for example, it used the XMM, which are not scalar registers, but they are the registers, 128-bit registers. But in any case, it is very tight to the YMM registers, which are the registers, 256 registers, which are typical of this extension. If you, for example, want to use this code with the AVX512 extension, so with bigger vector, you have to rewrite the code because, for example, the registers are called ZMMX. You are using Y. And so this code probably will run, but will not take the advantage of powerful hardware. So the RVV structure is very flexible. There is here just a recap also of the differences between vector unit and GPUs. There are very many differences. I just want to point out the fact that vector unit is better suited for low latency and medium throughput stuff. And it's more tight for when you have very control flow which is not very simple. It handles better the complicated control flow, while the GPUs are not adapted for complicated control flow. And another big difference between the GPUs and the vector units is that normally you have a very huge data transfer from the CPU RAM to the PCI because it's external. You have to let the data travels through the PCI bus to the GPU RAM, while the vector unit are inside very close to CPU. They use data directly from the cache, the main cache of the CPU. So also the power consumption is reduced. These are a recap of the limitation of the fixed width SIMD. Because it depends on the hardware vector width. So we have a poor portability and all the stuff we already saw. Once more, I want to point out that RVV shines when we have irregular and latency sensitive workload. So it's very common used for AI low-end product or the data DSP. Let's go. Okay, so what we are working on in Openchip regarding the vector architecture. Of course, we are using the latest available RISC-V extension, which is the RVV 1.0. This is the latest available in RISC-V. We use long vectors. We are trying to use as long as we can. We use the concept of a lane to increase data level parallelism and also some hierarchy improvement to have a higher level of data parallelism. For example, using multi-FPUs per lane or common memory, which is the high bandwidth memory, the HBM memory, and also using the concept of chiplets. And as the vector units are very tight to the scalar core, we need to use also some kind of instruction level parallelism too, so we have also some powerful out of order cores. I just did this picture to clarify the concept we already saw regarding how we can increase the data level parallelism, just to keep these things in mind. For example, you could start from a simple structure with 32 vector registers and 1 FPU. This is not very useful because you have to send the data one by one to this FPU. But in any case, the scalar processor sends the instruction to do operation on vectors and wait until the operation is finished and then reply back. So it works, also with the code we saw before. But you can decide to increase the power of this unit, changing the FPU with a SIMD FPU, so you can process more data in parallel, or you can add more SIMD FPU, and you can process more data in parallel. At a certain point, you can decide to go to the concept of lanes. What are the lanes? You can split this vector in pieces and do autonomous lanes which can handle the entire operation on vectors. If you want to increase the number of data, the size of the register, you just include more lanes and you can increase as much as you can the power of your chip. Then you can take this structure and replicate this instruction in a multi-core processor, and you increase again the level parallelism. And at a certain point, you can decide that this one is a chiplet, and you can have more than one chiplet inside on a silicon substrate, which is called interposer in this case, and you have a very high data parallelism. But you have to take in mind that at a certain point, you will face the problem of data retrieved from memory. If you increase a lot this structure, you have a lot of data you have to take from memory to fill all these computing units. So it's a compromise between the parallelism and the data you have to take, the bandwidth of your memory. So for that reason, most architecture, we are using the HBM memories, but these memories are shared between many chiplets, because you have to do some calculation on how much memory you need to handle all this parallelism. There are many solutions in the open source world regarding vector architecture. I reported here some examples. There are two famous long vector examples, which are ARA2 and Vitruvius, which is made by in the AP consortium, but by BSC. It was made by BSC. And also these three are very common, very famous short vectors architecture, also Lotus Spatz and Saturn. Also, Openchip is targeting to use these architectures with out-of-order cores and multi-lane, and as we saw before. But what is also important is that our company is also working on to further increase the computation, not only vector unit, but what is called IME, integrated matrix extension. So it's not a different concept. We are doing directly operational matrices instead of vectors, and it is integrated probably. Okay, it is integrated because I can show you later on. Okay, I put here also a block diagram of the Vitruvius Plus, which is the long vectors architecture made by BSC. And in my opinion, I studied very well this structure, this architecture. It's very educational because it contains, it's simple but contains every concept regarding the vector unit. I don't have the time to go through all these details, but you can see, for example, here the concept of lanes. These are the These bank are RAMs where the vector registers are stored, because vector registers are stored in this bank of RAM. There are some buffers. These are the computation unit. These are the interface towards the memory to retrieve the data from memory. And this is the part where you take the instruction and send the instruction to the lanes. I would have more time to discuss on this, but I would also want to show you the concept of the matrix extension, which is very, very, very useful in my opinion. Let's go to this. What is the matrix extension? The main problem. What is the main problem nowadays? It's that AI and ML, the machine learning world, is dominated by matrix multiplication. It is generally called the GEMM, and we can say that 90% of the time, for example, an LLM model is dominated by matrix multiplication. This kind of operation, in general, they are named fused, multiply, and accumulate, because you do many times A times B and then add the C without putting back the results to the target vector register. What is the real advantage of a matrix unit? It's the fact that you can use just one instruction to do a matrix multiplication. Otherwise, you should split the operation in dot product between rows and columns of the matrices and do many vector operations. And so you have to send many instructions. In this case, you just send an instruction. This is the first advantage. With one instruction, you can do an operation between two matrices. So you have a massive parallelism, but what is interesting is also the data reuse. Because if you think of the way on the way you do the matrix multiplication, you put data in matrix A, matrix B, and then, for example, do the multiplication, and you multiply the first row by all the columns. The first row stays always the same. So you don't need to retrieve every time this row from the memory. And so you reduce the pressure towards the memory on this data. So this is a real advantage of the matrix unit. And this ends to an high, what is called, this is a very used parameter in this kind of architecture, which is called AI, which stands not for artificial intelligence, but for arithmetic intensity, which is the number of operations, for example, of multiplication you can do, divided by the memory transfer. So but the memory transfer are the data you have from memory to registers and also from the registers to the memory. Currently, there are 3 different approaches to the matrix extensions, which are discussed in this task group in RISC-V International, which is an organization which tries to standardize all RISC-V operations. They are studied these 3 structures, the IME, VME, and AME. The IME is what is called the integrated matrix extension. This is the simplest one. We are working also on this one, also on these 2, but mainly on this one, because you want just to use the RVV vector extension to do matrix multiplication. We are thinking to a way to use the same registers, arranging the data inside the register in a matrix shape to do matrix multiplication. So you don't add any architectural state. I mean, you don't have to add any other registers and so on, just the same register or RVV. And you do the operation like it was a vector operation. The VME is quite similar, but it exposes another architectural state, which is the accumulator. So as I told you before, as you have to do A times C, B plus C many times, if you think you don't need to store back every time the C register, the C results to the register. If you design an accumulator, which is a local register where you store C, where you store C, you don't need to put back the C after every computation back to the register. So you gain a lot of bandwidth in this case, and you can go faster in any case. You are adding just this accumulator state. The AME instead is a totally new extension which adds, don't use the vector register, but just add other kind of registers which are called tiles. So you have new registers which can handle just matrices. So you don't need a vector extension because it's a totally different unit. Okay, this is the way, for example, these things are discussed in the IMTG task group. You can go also to the web and see all this discussion. They are free. This is the way the IME works. These are the registers, the vector registers. They are designed in this way, not linearly, because we are trying to arrange the data inside a vector register. This is, for example, B0 vector register. This is B04 vector register. You arrange the data in this way. In this case, it is what is called row major order. Normally, the matrices are stored in the memory. For example, in row major order, it means I store first row, and then sequentially I store the second row, and then I put this data in this order in this vector register. While I put in this order in this vector register, and the multiplication create this kind of results, which is composed of two vector registers. In this case, your hardware will specify just these two parameters, this parameter lambda, which is the size of these sides. And so, for example, your hardware could choose this kind of lambda and put any many computation unit to do this kind of multiplication. But some other company could decide to choose lambda equal 2. This vector register is the same of this one, it just arranged differently, but the number of elements inside this vector register is the same as this one. But if you arrange the data in this way, and in this way here, your result is a bigger matrix, so you do more computation with the same data. More computation with the same data. In fact, the results is put in 8 vector registers. So also here you have your flexibility to build your hardware as you can, choosing the correct lambda. You can design the hardware you want, and you will use the same the same vector registers to do this operation. Of course, this extension generates a new set of instructions, because we should add the instruction to multiply matrices. So we will have some instruction to do the operation between matrices, but using the same, almost the same RVB hardware. I guess we are almost over the time. I'm concluding. This is the last part. The programming model we are using for vector, going back to vectors. How you can program the vector unit, an hardware which includes the vector unit. You can use 3 ways of making your code. You can use the C++ intrinsic, which are specific function which maps directly to vector instruction. For example, I put here an example. You can add this high-level instruction which says I have a C vector which is this type in C is a new type, a custom type, because it's a 32-bit register with mal equal to 1. And then you do this operation. You want to add the vector VB, this type of vector, 32-bit. And you want to add A vector with B vector, and the length of this vector is VL. This is OK because you have quite a higher level of coding. but still you have a control of the register, because you are here specifying the register, the vector length, and so on, and you don't have to write assembly. But this code is not portable between different ISAs, for example, to ARM, to x86. There is also this feature. You can write code using the compiler auto-vectorization. You just write your code as you did before to do matrix vector operation. And then the compiler will unroll the code and detect if the code could be vectorized, and it could generate vector instruction if needed. But of course, you need to rely on the quality of the compiler in detecting this kind of patterns which can be done by vector instruction. But the beauty of this code is that it can be reused for different ISAs. Or what we usually do, for example, for AI or machine learning, is to write directly the assembly code, because you exploit the maximum power of your unit, because you write directly the ISA instruction. You have the maximum control and the performance. Of course, you cannot port this code very easily, but in some cases it's better, for example, for LLMs, AI, and so on, to use this kind of approach. We can jump this one because it's what we talked before. And the last slide is one example of the compiler, how it works in case of you want to do some operation coding for RISC-V unit with vector extension. You usually use a compiler, which is this one. It's, for example, for a 64-bit unit, you can use this compiler, which is a cross compiler. You just run this compiler on your machine, and then it generates the code. In this case, it's a bare metal code. This compiler will generate a bare metal code, so a code for a system with no operating system, which acts directly on registers and so on. And this is an example of the flags you can use for your compilation. You can use, for example, this flag, which is -03, which tells the compiler to enable the optimization, a high level of optimization. It allows to generate the auto-vectorized code if you use this flag, this switch. And you have here to specify the, you remember the code of the hardware we are using. You need here to specify the hardware you are writing the code for, which is, for example, RISC-V 64-bit hardware. G in this case stands for general level. It was, I guess this is the I extension, so the standard instruction set. Then you enable the compressed instruction set, and the V stands for the vector. So if you put here V, then the optimization 03 will generate the vectorized code. Otherwise, it will not. Okay, it was written in here. So, okay, and this is what we already saw. I guess I finished. I was a little bit rushing, but so we can say that RVV enables to do a very scalable vector computing. The vector length agnostics, the real innovation of the vector unit in RISC-V. So probably we will use more and more in the future architecture. And but another point is the matrix extension, which have a very good future, particularly now for the AI and the machine learning. Also because so far there is no standard for matrix extension. If you go to RISC-V and read the specification, you find the RVV, but you don't find any kind of standard matrix extension. There are many matrix extensions from different companies, but they are not standard, because another beauty of the RVV is that you can define your custom ISA. So some companies are defining their custom ISA for their version of matrix extension, but it's not a standard, and that the RISC-V international group are trying to generate a standard taking into account the studies, the versions many companies are doing. So that's it from my side, and I hope it was interesting for you. Thank you.
Okay. Thank you. Maybe, thank you, Massimo. So now maybe it's time for a few questions. If,
of course.
Yeah, there is still some time, so can't get a micro. Well, on the one hand, if you study computer architecture, you know, I guess you understood more or less everything that he talked about, and that's nice because it means that you can work tomorrow in OpenShift. So that's important. But we are also working at research level on some similar features there, and some questions that arise me is mainly about the memory hierarchy, and you showed this Vitruvius picture, and I'm a bit blind, so I couldn't see the details, but there were no caches, so it's mainly DRAM banks directly connected together, connected directly to the register file.
Okay, this was yeah. We have really here you see OVI because they have an interface which is open vector interface which connects these units to the memory. So they are connected through an interface to the memory which is in the processor. So it's not optimized in this case. So probably, in fact, we will not use this kind of approach in our vector unit because the data should pass through this interface, so through this OVI interface. Yeah. So the bandwidth is, of course, reduced. So for this reason, I said this is more educational, but it's not that much optimized.
So then in the picture, those banks are register files, so they are not...
this one?
This one, yeah.
No, this one are the RAMs which contains the vector registers. So it's a RAM inside the vector unit. It is a RAM.
It is RAM, but they're used like a register file.
Yes. Okay. Yeah, it's because of the size. You can compact the size, and because you have a very modular structure. You see here, you have this RAM is 5 banks, 64-bit. Then you read 64-bit from each bank and send this data to this buffer before going to these two units, which are one the floating point and the other one is the arithmetic logic unit. So this structure is very tight to the way they realized also this architecture. Choosing 5 banks, it's not a good choice because it's not a power of 2. This was my first thought when I saw this structure. But I can say this choice of 5 banks is strictly related to the FSM, because the FSM cycles through 5 states. So it's kind of related to this. Yeah, it was just to be simple, to don't do a more complicated arbiter for because usually now you used to generate an hardware with some arbiter which takes data from the bank in a different way, not just with a simple FSM.
And what's maybe like if you can get more or less latency, more bandwidth, more banks to get more parallelism, what are the main directions you
in this case,
or in the main memory?
In this case, you can increase the number of lanes for sure. If you want, you can add more FPUs, more LEUs. What we are doing is this one. You can put 4 or 5, but if you put more of this one, you have to arrange probably this bank differently because you have to take more data from these RAMs. So, or you have to add more banks or to arrange this bank differently.
But also you will need more bandwidth through the
Yes,
the memory
you need
system.
from more band. Yes.
Because then I understand data from the memory system has to be distributed across lanes.
Exactly.
Because your architectural registers are mapped into those banks.
Exactly.
Then I guess it's also kind of out of order. There is something out of
Yeah.
order there.
Yes, this is out of order too. Yes.
So then you need.
Yeah, because you see here you have the renaming unit, the reorder buffer. So this manages the out of order execution. Yes, and you see also some other details here. You see the ring node because the registers here are split into lanes. So, for example, for some operation, the permutations or you have to pass data from one lane to another one. So that's a problem because the vector registers are split in different lanes. So until you remain in this lane, it's very simple. When you have to pass data from one lane to another one, you need to add this ring, which is a big bus, which pass data from one lane to another one. But it is not very fast because you cannot build a 120-bit, 1,000-bit bus, otherwise it is too much. So it is also a problem. This ring, it is something which can be done in a different way. But it is needed because of the vector registers split on different lanes.
Okay. So I have many more questions, but because it's almost 4 o'clock, last opportunity for you to ask a question.
Yes.
No.
I wanted to ask you about
Yeah,
the vector mask, which you explained that if you put a 0 or 1, depends on which data you want to execute. It means that the data mask, you have to put it manually, or there is any algorithm that you can select it automatically?
No, you have an instruction which loads the V0 register, which contains the mask, and you can put the mask there. And then you just send the instruction, the classical instruction with the operation you want to do. Could be an add operation, a multiply operation, and you have to specify as last parameter the register you are using with the mask. It was V0T, for example. So there are two instructions: one to load V0 with the mask, and then the other one to say this operation is a masked operation. And in the instruction, you have to clearly specify which is the V0.T, which is the mask vector. That's the way it works.
Yes, but you have to specify it manually, like put 0 1.
No, you can just load by, for example, you have in memory the mask, and then you load from memory this mask. Yes.
Okay.
Like a normal.
I think you can do both. So you can compute the mask.
Yeah, both.
If you have like branches, you have
Yes.
anything else, you can compute a mask and use it so that you are, if the condition is true, you are blocking the else part of the vector. So if you're in some units, you are doing the then part, and in other parts you are doing the else. You would have compute the vector mask and you use it.
But you don't need to use like bitwise operation. There are like, you can compare two vectors and get a mask out of it. Like if you want to process only elements that are larger than 10, then you can first make the comparison, then you get your bit mask, and that's the one that you use to decide which elements of the vector are used or not.
I think you also, in the example you showed, so there was no tiling loop, no tail loop, sorry. So I think that the mask was there automatically compute.
Yes. Yes.
So when you get
The tails or the tail of the vector in the computing loop, you are saying
they use the masks for the last loop iteration if it's not multiple of
the vector
length.
length.
Of the vector length.
Yes,
Okay,
that's
also this VL and VLM and everything, so that you know the size, the real size of the vector, and so for the last iteration, the tail is computed automatically.
Yeah, that's what I mean.
Yeah.
So so it was the first instruction because you don't know it's architecture independent, so you don't know with the same instructions, you don't know the vector length. It should work with several ones. So with the first instruction, you get how many computations are going to be done in each loop.
Exactly.
But the last operator is a mask, I think, or not.
No.
Am I confused?
Where? Here? No, it's not. No, there is no mask here. No, it's simply if the VL is shorter than the maximum VL, it's automatically masked. If you don't specify in your operation if TA is 0, 1, I guess the default is 1, so it's tail agnostic. So you don't need to care. Automatically, it doesn't compute
so
the tail.
There is automatically set.
Yeah.
Okay.
If you want to specify explicitly what the tail should do, you have to specify TA in the instruction. I guess it's not specified here. It's when you do the add, I guess you have to put also the TA parameter if you want. Otherwise, it is agnostic by default, I guess.
And for just one question for the matrix extensions, is there a special load to pack the vectors there with that kind of layout, special layout? So you don't have to do it manually. Is there a special stride that is non-linear stride?
Yeah, one idea is to have a specific instruction to load the matrix in that way. Or because you, in any case, have this lambda which define the way you load your in any case, you have a different instruction.
Yeah,
you have an instruction like tile load, it is called. It's not a vector load, it is a tile load. This could be a way, but it is still under definition how many parameters should be defined during this instruction. For sure, lambda should be there, and probably is in the CSR as in the control register. You have to define before lambda, as you do with vectors. You define lambda, and then you can send the tile load, and automatically the data in A will load in this way, and in B, you see, it's a little different. Yeah. And that's a problem here, because usually in memory, data are stored row major order. You want to load here column major order, so you have to do a stride load, and it's not really a good idea. But so far,
stride load also in V00, because you fetch four elements on a row, and then 4 elements on the next row, and then 4.
Yes, because this is yes. In this case, it's in this way. In any case.
Yeah,
but
it's related to the memory access.
But at least you have 4 consecutive elements here, and probably they are on the same.
There you have it worse on V0.
But this is really a problem. This one.
Thank you.
We need to wrap up, but we can continue the discussion later. So thank you very much. And una última cosa, te he puesto un aplazamiento. Si alguno de los que habéis llegado después necesita el QR para Copa de las Casas, lo tengo por aquí. Y si no, muchas gracias a todos. Otro aplauso para Massimo.